Welcome everyone to the Ancestry of Polymorphism in Clojure by Amogh Talpallikar. We're glad Amogh can join us today. So without further delay, over to you, Amogh.
Thank you, Yogesh. Hello, everyone. It's 5:30 in the evening in India, and if some of you are joining from other parts of the world, maybe it's a little too early for you in the morning, or if it's towards the east, it's almost evening for you. If there was a way for me to wish people as per their time zone, then it would have been so nice, but I am not polymorphic that way. So we are starting this session. I'm going to talk about ancestry of polymorphism in Clojure. So essentially what I'm going to do is we are going to basically do a story of polymorphism as an idea, as a concept, starting from the very genesis of the idea, which happens to be in biology, in nature, and all the way to the form that Clojure offers in its programming API. Before I start, I mean, what's the motivation to do a talk like this? Number one being Clojure. I've been using Clojure for 8 years now. Uh, I work at HelpShift, which is a customer support automation platform, which is SaaS organization, and the backend is entirely written in Clojure. And for over 8 years, I have seen, you know, a big code base being written, maintained, changed over time. That is entirely written in Clojure. And there are some learnings from the way we go about it, good and bad both. And second motivation is, of course, curiosity. I'm a curious person. When I first started using Clojure, I didn't know much about the language. And I mean, any programming language, you can never be an expert, right? How much you learn it over time or use it over time. So I kept discovering something new. I still discover something new about Clojure every now and then. I use it. And one such occasion was there when I ended up exploring how polymorphism works in Clojure. And I found some hidden features, at least they were hidden for me because I had not explored the language that deep. And I found them interesting. So, as curiosity in me wanted to know, are these Clojure ideas or have they come from other languages that have influenced Clojure? So of course, Lisp is one possible suspect. So I went back to see how polymorphism happens in Lisp, and kept going back and back and back. And then I found myself in a rabbit hole, which was polymorphism in nature, and I like telling stories, right? So what we are going to essentially do is that the entire traceback that I did, we are going to now follow that journey back and see polymorphism as an idea shapeshift into the form that Clojure offers today in its API. Okay, a little something about Clojure for people who do not have a background, and I will make it quick for people who already know what Lisp is and what Clojure is. So Clojure is a Lisp, and which means the syntax basically looks kind of like this. This is an S expression. It's called symbolic expression. So most of Lisp code, there are many Lisp dialects out there, and almost all of them look kind of like this. Uh, it seems a little weird at first if you're used to seeing the plus operator as an infix operator. But Lisp is known to have this consistency in its syntax, where first thing is the name of the operation, and rest of them are the arguments, and it is represented as a list if you look at it carefully, which allows Lisp for very powerful metaprogramming features, where if you do not evaluate expressions, you can just treat them as a list, which means you can use Lisp code to modify a Lisp code as if it was a list and turn one code in one form into another, and lets you make DSLs and uh, gives you lets you bring new syntax into the language without waiting for the language designer to go through the whole process of having a proposal and then having uh, a compiler come up or a runtime come up that implements that proposal. That's the power of Lisp. That's the power of most Lisps. Clojure is functional. Functional in the sense that functions are first-class citizens. Functions can return functions. Functions can be passed to other functions as regular values. Is a classic example. Yeah, there is a square function and defined using the define keyword. Uh, then you can see that function is being applied to a list of numbers to square every number in that list using the map higher order function. It's a pretty standard thing in most functional programming languages. It's there in Clojure as well. It's not just this. Clojure gives a lot of importance to immutability. By default, all data structures in Clojure are immutable. And so every function, when it takes an argument, returns the evaluated expression. And there is some neat optimizations done under the hood to make sure that this doesn't blow up in memory or in terms of performance in any other way. Another thing that is very close to Clojure is Clojure is a dynamically typed language, but the philosophy that or the idiomatic way of writing Clojure is that the data modeling will be done using maps. And it's a convention where, like, you can define a person here. You have a bunch of attributes and the values against it. And that's what the Clojure philosophy is, that you keep things simple. If you have associative data, define it using a map. And if you have something sequential, define it using a list. And essentially, it's as simple as that. Clojure is hosted on the JVM. Clojure has actually three known targets. One is the Java virtual machine, which is the most popular one, and then there was JavaScript. So there is a port of Clojure called Clojure script that compiles to the JavaScript source code, so you can target browser frontend as well. It plays well with Java, so wherever Java is used, theoretically Clojure can be used there. And there is a CLR implementation as well, and there are lots of other implementations that community has contributed to words. And it's been more than 10 years now. I think it started in 2007, so more than 15 years of Clojure already. So that was about Clojure. Let's look at polymorphism as a concept. Uh, Polymorphism, before it entered computer science, was a term that only biologists would use. And it's not surprising that it's like with most things, it starts with nature. Polymorphism essentially means it has roots into Greek words. One is poly, which means many, and one is morph, which means form. So essentially anything that is there in more than one form exhibits polymorphism. On the left, you can see two jaguars. One is a little dark, and the other has a golden coat and has some spot patterns on it. These are both jaguars, but they exhibit different physical traits. And this is essentially known as polymorphism in terms of biology. Okay, let's study the two jaguars a bit more. And if you see, what happens is that in biology there is this concept called phenotype, which means if you pick a species, could be plant, could be an animal, uh, And things have attributes, right? Even living things have a lot of attributes. So we typically look at attributes, and we see uh, a certain set of attributes that remain the same for that species. And there are certain set of attributes that show light variation. And those set of attributes, like in this case, code color and pattern are those attributes, are collectively known as the phenotype. So there is no type as such. You have a set of attributes which are collectively called phenotype here. And there is a name that is given to the two commonly occurring phenotypes. One is the melanistic jaguar, also known as the black panther, and the other is the spotted jaguar on the right. So in nature, you don't really have finite types. Everything has attributes, and but then the question comes, why do we categorize and generalize? Right? We categorize and generalize because our minds find it easier to process information when we put them in boxes. And when we generalize things, we can make quick decisions about those aspects of those things. And we have been doing that even before, we had computers, and most of our processes in the industry or in academics started becoming digital. So that brings us to polymorphism in computer science. So polymorphism in computer science really uh, started way back in 1966. It didn't really start, it was observed and called polymorphism then. Uh, person on your left is Professor Christopher Strachey, who was working at University of Cambridge with a bunch of folks on an experimental language called CPL. And CPL is an important language to know about because it didn't really got fully implemented and never really saw the light of the day. But a lot of concepts around how high-level programming language should be, what concepts there are, were first thought about uh, when this work on this language was going on. And Christopher Ritchie actually went around teaching at various universities in different countries across Europe. And then what he did was his uh, lectures that he used to take had notes, and those lecture notes were later on compiled and put into a paper, which is known as Fundamental Concepts in Computer Programming. A lot of our core ideas have come from there. So that's why you see CPL influenced many intermediary languages all the way towards on the way to C. And that's all about CPL's origin. Let's look at what CPL said about, or the CPL folks said about polymorphism. So in the paper, uh, it talks about four concepts, and we will focus on them first. On the left is I talked about assignment operation. We are all familiar with this. Uh, so there were two concepts associated with the assignment operation. One is called the L value and the other is R value. Essentially, anything on the right hand side of the assignment operator is R value, and anything on the left hand side of the assignment operator is L value. It's typically a variable which points to a location in the memory where something is stored, and R value is something which is evaluated and then stored in that location. So that's the concept of, people who have used C know that the quite often the terms L value and R value have been used in the context of C quite often. And these concepts come from CPL. Now, why? Then the second concept that was being actually thought about, which wasn't thought about a great deal until then, was the idea of type. And the CPL team said that type gives us three important pieces of information. One is storage. How much space does the type take in memory? The other is the range of values that it can take. And it also helps the compiler to check for errors, right? You're not multiplying two strings essentially. So those kind of extra benefits you get out of types being available at compile time. Now, type knowledge was classified into two categories. One was manifest, one was latent. According to the paper, manifest is essentially anything that is available at compile time. So if type information is known at compile time to the compiler, that information is called manifest. And if the type knowledge is going to be gathered at runtime, or anything that is going to be known at runtime, right, is called latent, because it will happen a little later when the program runs. Which brings us to the basic idea of polymorphism that the paper talks about. You can see there is a addition operation happening here in the fourth section of polymorphism. This is polymorphism because if you see, when you're adding two floating point numbers on the processor, floating point arithmetic has a separate instruction set in assembly language. And same for adding two integers. That's a different instruction. And when you're adding an integer and a floating point number, compiler has to do even more, because when it has to upcast the integer to a floating point number and then add them. And this very nature is something of the plus operator or any arithmetic operator was called polymorphic by the CPL team, because it hides the underlying detail and gives you a nice interface where you can just use the addition operator and not worry about how the addition actually happens underneath, right? So yeah, that's polymorphism. So there's a problem with polymorphic functions. And the problem is that because CPL was a language that at that time chose compile time types, basically manifest. And the problem in this situation is that when you're dealing with polymorphic operators like the plus sign, it's hard to figure out what is the type of the expression at compile time without knowing the values. And for that, you have to have ad hoc rules, right? Like here, you could have a rule where you say, if both the operands are integer, then the result will be an integer. If both one operand is integer, the other is float, then you have to do upcasting, and then both are float, and then it's a float. So it's not very systematic, and then it adds some complexity, some logic to the compiler. And that's something that they talked about in the paper, which led to classification of polymorphism into two broad categories. One was ad hoc, which we saw. Basically, you have type-specific versions of the same function. Like the signatures of plus sign that you see are from C++. And looking at the signature, typically you decide at compile time which version of the function will be invoked based on the ad hoc rules that are there. The other way of doing this is, and this is there, like, in other languages today, type classes in Haskell is an example. Method overloading in Java, function overloading in C++ is an example of it. The other way of doing this at compile time for the compiler to know the type of the result, one way to go about it is to use parametric polymorphism. What do we mean by parametric polymorphism? If you look at the signature of the map function here, what does a map function do? It takes a function and it takes a list and returns a new list. And it applies the function on every element of the list. So essentially, if every element in the first list is of type alpha, and you apply a function that accepts an alpha, returns a beta type of value, then the new list that you will get is of type beta. It can be anything. Those alpha, beta are just placeholders, are very type variables. And you could write an entire algorithm without actually specifying which type it is. And only when you're invoking the algorithm, you specify which exact type is in question. And most of the code remains generic. And that's why it's a more systematic way of writing generic code. It's not really polymorphism in my opinion, because programmer is not writing different implementations of the function. So there's only one form that exists, but because it's a template, it has variables, it can effectively do many things. So I think the aspect of polymorphism that is important are the abstractions it creates and the simplicity it brings, and the generic algorithm that you can write. But what about dynamic types, right? So the paper also talks about the opposite extreme, which is essentially what it says is that if your type is known only at runtime, then you don't have this problem of trying to compiler having to figure out which version to link to the function call. So what the paper said, right? The idea is worth examining. If you ensure that everything takes uniform storage, then you don't have to worry about storage that the types tell you. And if any type accepts any value, then in that case, you don't have to worry about the range at compile time. But only at runtime, which means the object, the R value, has to carry the type information, and the runtime will have to determine the type of the object and decide which version of the function has to be invoked, which at that time, based on the kind of CPUs they were, it seemed like was an expensive operation, would make programs slow. So this is something that Christopher Strachey wrote in the paper, where he basically says is that this dynamic type determination will slow down programs now. But the idea should not be rejected, because maybe today's computers are not ready for something like this. But maybe years later, there will be, better hardware out there. And we know that dynamic type determination exists today. But he kind of said this in 1967. That kind of gives me goosebumps even now. Okay, so now let's come to how did we get into runtime polymorphism eventually, right? So we are in Norway, somewhere in 1960. You have Kristen Nygaard. He works at National Defense Research wing of the Norway government, right? And what he is doing is trying to build complex simulations for years now, using the programming languages that were available then. And he feels that those such simulations, there's a need to of a language that can simulate such events at a much higher level. So he imagines a language that can, process events that are coming in, and he uses the concept of station as something that processes uh, ongoing customers. And he has a very high level visualization of such simulation. And he thinks that Algol was a popular language back then, and he thought that we will use this language and we will build everything on top of it. But this never really had a stable definition. So he sought Ole Hondal, who he had worked with before, and with him, because he was an expert at designing programming languages. So he put his idea forward, and together they started working on the language, and they gave it a name, Simula. And by 1965, Simula 1 was ready. So it had this concept called activities that would be instantiated at runtime as processes. So a Simula process was an entity uh, which which had its own state, and could do its own processing, and had this capability to hold and wait, much like the coroutines today, hold and hold the operation that is going on. And that was essentially Simula 1. It was meant for discrete event simulation. And for that, heap-based storage was also something that was added on top of what Algol provided. And it gained quite a lot of popularity in the academic uh, scene. And by 1965-67, there was this feeling that, the idea of uh, having things as generalized entities is a good idea. And we could make a more general purpose language if we strip down some simulation specific features from the language. So they started working on a newer version of Simula, which was a stripped down version. And they were really inspired by the idea of Sir Anthony Poor's concept of records. So he had a proposal where he talked about how records can be stored and how one record can derive out of record and can share some common properties. This is something that they really liked. And eventually that led to Simula 67 by 1968. And you had classes, subclasses, as we know today. Nobody was calling it object-oriented programming. And yeah, and then you had virtual procedures that brought dynamic dispatch. So this is how Simula code kind of looked like. So this is how Simula looked like. You can see there are two classes, circle and rectangle inheriting from shape, and there's a virtual procedure area. So essentially what virtual procedures do is that you have a class hierarchy. If you call the method on the object, it checks the type of the object and then goes up the hierarchy chain till it finds a concrete definition of the method there and calls it. So, and they're called virtual because at compile time, the linking doesn't happen. So compiler leaves it for later. So what's the legacy of Simula? We know the story. Simula brought the concept of objects, classes, subclasses, which also inspired Smalltalk, which actually coined the term. Alan Kay actually coined the term object-oriented programming, but the focus was more on encapsulation. He came from a microbiology background, and he saw objects as cells, having its own state and passing messages to uh, each other, and the program moving on like that. So that was essentially Smalltalk for you. And Objective-C tried being close to the Smalltalk's syntax with as a preprocessor language with C. But with C++, Java, C Sharp, we essentially had the model that Simula came up with, and some of the ideas of Smalltalk were dropped there. And but the term object-oriented programming was associated with all the languages that we see here in the green. But how did uh, what was the Lisp community doing, right? Because if you around that time, Lisp community was also interested in having some object-oriented features in the Lisps. So what happened was somewhere in 1979, at MIT, there was an effort to add some object-oriented features to Lisp. So there was an extension because, as I mentioned, right, you could extend a language with macros, and you could come up with new things in the language without having to come up with a new version of the language. Extending Lisps is very easy. So an extension of Lisp was there called flavors. It tried bringing Smalltalk like message passing to Lisp. So if you can see the syntax, right, there is a fun call where you can pass the object to which a message is being sent, and that method is essentially the message being sent to the object. Then there was loops in 1983 at Xerox PARC. And it was closer to what Alan Kay wanted in object-oriented programming. And so that was there. And somewhere in 1980s, what happened was these two languages for which flavors and loops were, as extensions were developed, the MacLisp and the InterLisp, were dominant dialects of Lisp. And there was a lot of fragmentation in the Lisp community. And more Lisp dialects were coming up. And there was a need for standardization. So a lot of people came together sort of over a specification and said, how Lisp should be. And a lot of ideas from different versions, variations of Lisp were brought together under a standard. And that's what we call Common Lisp today. There were also, when this standard was being built, there were a lot of competing styles of object-oriented programming in Lisp. There was new flavors that introduced uh, a generic introduced generic methods instead of having the message passing syntax. Uh, then generic functions typically dispatch based on the first argument. So it's kind of like object dot method, but you typically pass object to the as the first argument to the method. That essentially it was. Common loops was another new proposal, and they wanted to be able to dispatch on all the arguments, not just the first argument being the special one and having a function. And finally, you had by 1988, you had a standard called Common Lisp Object System, and it combined a lot of these ideas into one standard. And it was there from the ground up because every type in Common Lisp uh, after that was an object, and it wasn't like an extension on top of Common Lisp. It was rewritten from the ground up to be an object-oriented language where everything is an object, very much in the Smalltalk style. So this is how CLOS kind of API looks like. This is how so I will give you a use case. What we have a use case here where what we are trying to do is that there is a uh, application that send messages to users, and based on the plan of the user, right? Whether it's a free user or a standard, or the user is on the standard plan, or it's a premium user, it can send the logic changes what it can do, and you have to send message to this user. And the use case is that it goes through various channels. Your API provides SMS as a channel, email as a channel, push notification as a channel. So your logic should take the combination of user's plan and the type of the channel in mind, and then based on it, dispatch. So keeping two things in mind. So this is the syntax that we have for Common Lisp. You use def class to define a user class and a channel class. Free user, standard user, premium user, all derived from the user class. It's inside a list because Lisp supported multiple inheritance, so you could have more classes there. And then you have a hierarchy for the channel type. Right? And this is how you define a generic function in Lisp, where you define it using def generic, which means it's a family of functions defined using def method. And it says it accepts two arguments, which are of these two types. These are classes that are shown there. So these should be classes. And then you can have many versions of it. And based on the type of the argument, and it also looks at the hierarchy. So it tries to find a version which is more specific and closer to the arguments that are passed and calls that version. And there is a way to do catch-all also, where if you provide the parent class for everything and don't implement anything for the child class, then it matches the top level function that essentially catches everything. So this is how you use it. You're defining users, channels, and then you just call. This one had defined a multi-method, so that got called, but email channel was not defined, so it went to the catch-all block, and that's where it went. So that's all the idea is. Now, if you want to simulate this in a language that doesn't support this kind of dispatch, where you're dispatching based on uh, all the arguments of the function, which is the standard languages has followed the Simula model, all object-oriented languages. I will take example of Java. It's familiar to a lot of us. If you want the ability to, because in Java, if you call a method on an object, it will look at the object's class. It will not look at the arguments class and figure out which version of the method to invoke. So people typically use a technique called double dispatch. So as we saw in Common Lisp, you could invoke a function, a polymorphic function based on the type of all the arguments that are being passed to at the function call, right? Uh, to simulate something similar, at least with two arguments, there's a technique called double dispatch. I try to solve the same problem using double dispatch, which uses a design pattern, which is very popular for doing this, called visitor pattern. So you essentially define two interfaces. One interface, like here, is plan. It is something that you are visiting, which is the other hierarchy. It accepts a channel visitor. A channel visitor is basically another interface that has a visit per uh, the other thing that it is going to visit, which is in this case are users. So it will have an implementation. So anything that implements, basically all channels that implement channel visitors will have to implement all the visits for each user. And all the users will have to implement the accept method, which basically accepts the visitor and calls visit on it. And that's a trick. Basically, uh, this is how you use it. You make your users, you create, instantiate visitors, and then you call user.accept and you pass the visitor. So what happens is that when a visitable accepts the visitor, a dispatch happens. And what happens is that the accept will go to the appropriate, because of the dispatch mechanism, will go to the appropriate accept of the concrete class, will pass itself to the visit method, which it invokes on the visitor. So when it invokes visit on the visitor, the second dispatch happens, hence the name double dispatch, right? It's not really multi-dispatch. Dispatch is happening twice, one after another. And there are drawbacks to doing it this way, because if you have to add a new channel here now, right, it's easy. But if you have to add a new plan, then you have to update all the channels and add a visit method for each channel. So there is a trade-off here. And if you have three dimensions, right, instead of two, if you have to do it with three arguments, right, instead of two, it's much easier in multiple dispatch. But here, I guess you will have to do a nested double dispatch to make that happen. Now let's look at what Clojure says. Now we have arrived at Clojure. So Clojure's philosophy kind of dictates how, because if Common Lisp had everything solved, right, in terms of multiple dispatch, in terms of polymorphism, why would Clojure change anything? Because it's a Lisp after all. But Clojure community was opinionated. Rich Hickey was the founder, had a good reason the way he wanted to go about. Uh, I will just talk about polymorphism in Clojure, right? So one core idea in Clojure is to define entities using maps, or if a sequential entity, use lists, right? Basically, these are just values. It's data. Don't treat this as concrete types. And you have lots of functions that can inspect these data structures and make decisions. So Clojure's way of going about it was not have classes, the classical object-oriented programming. Uh, Clojure has a derived form. What you can do is you can essentially, if you want to have a hierarchy, you can have a hierarchy of values. So these are keywords, normal keywords in Clojure. So keywords in Clojure are essentially constants, you can say, that evaluate to itself. So they're typically used as attributes and as constants in the language. When it comes to data modeling, you can use them for enums as well. So here you have a derived form that basically takes a global registry and adds this hierarchy, which would you typically do with classes, right? And free, standard, premium have one parent, and email, SMS, push have one parent. I have kept the parent same for for simplicity. You could have two separate values, right? One keyword forward as a parent for users and one for all the channels. You could have different value there. You could actually take Java classes because Clojure interrupts with Java really well, and bring them to this ad hoc hierarchy at Clojure level as well. And then even Java types will work well. And then you define multi-methods, which are very similar to what we saw in Common Lisp. But the difference is that this is more functional because we have a def multi form for send message instead of a def generic, and it accepts a lambda, which is basically a function that runs on the arguments that are being passed and returns what is called a dispatch value. And then there are multiple variations of the same function tagged with the possible return values that are there. So if you want multiple dispatch, then you can have a vector with multiple values in it, or you could just have a single value, which could be anything. And or you could actually have a Java class also. So it respects that hierarchy as well. So what happens is that when it doesn't really check for equality. First thing it does is checks for equality, right? Like, for example, you call send message with these arguments. This function is invoked on these values. And so here in this case, a vector is returned of user's plan type, which is extracted out of the user map that we saw earlier, right? Here. And the channel that is being passed. And then based on it, a multi-method is essentially invoked. So here I've only written one multi-method. You could have many methods with different variations out there. And Clojure, what it does is it doesn't do an equality check when it is doing a match. It uses an is a operator. It's a function in Clojure that takes the dispatch value and recursively sees. What it does is it first checks uh, if there is an equality check, then directly calls that version. If no version matches the equality check, then it tries to see if it's not being equal, then it checks if there is a hierarchy in play, using the derived type. If that doesn't work, it checks for whether if there is a class hierarchy in terms of the Java world that it is hosted upon in play here, and tries to call the more specific version of the function. And that's how. And it's an expensive operation, obviously. So there is some caching at Clojure level of dispatch value to the method tag, which the method version has been tagged with, so that this thing doesn't happen again and again. So there is some performance optimization there. And of course, there could be a catch-all clause if it doesn't match anything, because we defined any as the parent of everything in the hierarchy for all users and channels. If it doesn't match anything, it would definitely match this. And this could be your catch-all clause.
Amogh, I think we are over time.
We are
Yeah,
towards
sure,
end.
sure.
So other than multi-methods, which are a little expensive, a later version of Clojure, which was Clojure 1.3, I think, that came in 2010. And what it did was it brought a very Java style of single dispatch mechanism in Clojure, so that you could tap into JVM level optimizations. So you can see a protocol shape here, which basically compiles to a Java interface, generates a Java interface. And then you can have records that implement the protocol and give concrete definitions of the function, like area in this case. And concrete classes are generated for both the records. So basically, when they're running, it's a Java class and Java interface at play. So any inline caching or JVM level optimizations that are available to us are used. And it's obviously faster than multi-method, but sacrifices a lot of expressiveness that multi-methods offer. So essentially what happens is that you can, like in this case, what you can do is you can use multi-methods for core business logic that keeps on changing, but an implementation in protocols and records, if it is something that is in hot code path or is inside a library that your users will not have control over, something say that interacts with third-party APIs or databases, right? If the performance really matters to the users of the library, then they will not be able to do much in that case if you use multi-methods. But if you can predict that, it's a trade-off, matter of trade-off. But generally, when it comes to business logic that changes too often, every other iteration, I think an implementation in multi-method is just fine and doesn't really affect the performance a lot for most web applications. So let's do a quick recap of what happened until now. In 1958, we had Lisp with garbage collection. In 1967, with work on CPL, the concept of polymorphism was being talked about. Just a year later, in 1968, runtime polymorphism was available. And by 1988, you had Common Lisp Object System with the idea of multi-methods. And in 2007, you had Clojure. And 2010, you had Clojure protocols. So essentially, it took us 40 years from the idea of polymorphism in CS to Clojure, which basically means a lot of these ideas were already there, but for various reasons couldn't actually see the light of the day because perhaps the machines at that time were not strong enough, or the environment was not conducive. Maybe there were some business constraints at that time for some of these ideas to prosper. But it's a good thing that people write about those ideas. And it's a good thing for us to revisit some of those ideas. That's the importance of, CS history essentially, is that you look back at ideas, what people have written in research papers, and learn from it. And maybe some of those ideas are really applicable today. When the environment is more conducive, there are better machines available, there are better opportunities available for those ideas to actually become real. And that's all I have.
Yeah.
Thank you.
Thanks, Amogh, for the awesome session. Thanks, Amogh. Thank you all.